Hello everyone and welcome to our lab number 10. So in our lab number 10 and lab number 11, we are about to discuss the fundamentals of MATLAB. So MATLAB is basically a software plus a simulator in which we can verify and validate our circuits by means of various methods. For example, in MATLAB, we can also program our problems, which may be based on electrical or electronics component, which can be mathematically explained, and we can program that into our MATLAB script, and we can take useful answers from them. Other option is that the graphical interface unit for MATLAB. So that portion of MATLAB is called Simulink, which would be covered in the next lab, which is lab number 10. So in that lab, we'll use the graphical interface unit and we can draw our whole circuit or maybe anything else, maybe some mechanical system, maybe some electrical system, maybe some hydraulic system, anything. There are a lot of features and we'll be talking about that in this lab. So we can actually draw those features and create those models in Simulink, and we can run those models for a little bit of time and we can observe what those models generate as a result, and we can take useful advantage of how those systems behave when we actually simulate them. So yeah, so MATLAB is basically a very advanced tool and it's very useful in analysis of many different engineering and scientific problems. So in this lab, what we are about to do is to understand and let's recap the fundamentals of power system, power analysis on related to what you have studied in your theoretical lectures. And let's try to implement some of the very basic concepts of those concepts in AC power which you have studied into MATLAB script. So first, a little background of what AC power really meant is that it consists of two types of powers or two categories of the powers in which we can briefly segregate these components into. One is active power and one is reactive power. So active power is actually the power actually consumed by component, for example, a resistor. So when you provide the resistor a voltage and a current, what happens is it actually dissipates those energy which is provided to the resistor as electrical energy, and it dissipates that amount of electrical energy into heat, right? So that is actually the active power. So whatever you supply to the resistor actually consumes that power, maybe convert that power into some other nature of power, not electrical energy, right? Unlike that, a reactive power absorbing or delivering component is somewhat like a resistor or a capacitor. So it may be consuming power for a little time and it might be storing in itself in the form of electrical field or maybe in the form of magnetic field. And when you have removed the supply of voltage and current across those components, so what happens is now those components would be acting as a source and they would be providing energy to the circuits. And there is a huge debate on that, and we have already discussed that how the response might differ when a different component is subjected to different voltages and different currents. So such power which actually is seems to be absorbed by the component but not actually being actually consumed by the actually stored in some form of electrical or field or magnetic field, and it is always recoverable to serve back to the circuit again. Such type of power is called reactive power, and the power which is totally consumed and utilized by some component is called actually your active power. So unlike the previous case, So unlike the previous case, I have already explained in uh, sort of an analogical example that if there is a stream of river and the river contains the water flowing from a high hill station to a low hill station, and the water which is being flowed is actually the active power which is being continuously supplied to one terminal of the unit to the another terminal. But let's say if you dig down a small tank in between those streams and some water gets stuck into that stream, so that actual reservoir of water which is being stored in some sort of form in that stream is actually your analogous to your reactive power, which is temporarily being stored in that stream. And once the flow of water gets stopped, that storage can be used to recover that amount of power which was being utilized or stored initially in the form of reactive power. So these are actually the behavior of components in which they absorb power. So there might be possible some components as a combination of active and reactive power. That means they might be consuming or delivering reactive or active power simultaneously. So they are usually not devices which are purely active and purely reactive. These are actually the combination of both. So these are actually not subjected to the devices which are purely active and reactive, but this is the nature of power which is being associated with devices and the characteristics of devices which actually resonates with the characteristics of active and reactive behavior. So the overall impact, if you see, so what happens mathematically is we represent active power as a real component on the mathematical scale, and we represent reactive power as an imaginary scale on the y-axis. So of course, if active power is on the x-axis and reactive power is on the y-axis, there is always a resultant component which shows apparent power, which you can see in your slide here. Alright, so here you can see in your slide that we have an apparent power here. So what this apparent power is, basically we can easily find out using Pythagoras theorem. This is your base, this is your um, perpendicular, and the longest side is your hypotenuse. So you can always like go through the Pythagoras theorem, and you can always calculate these in terms of S is equals to P square plus Q square, that is the square of the active power plus the square of the reactive power gives you the apparent power. So in that way, the apparent power S actually represents a picture, a complete picture of a component, that in what combination, in what ratio it actually behaves as an active resonator and as a reactive resonator. So, so how much is it consumes or delivers an active power, or how much it consumes or delivers a reactive power. So that is actually your apparent power, which is represented as. Again, the angle between the active power and apparent power is actually your theta phi, and if this theta is 5, then the angle, then the side opposite to this angle is actually your perpendicular. And if you know what is perpendicular, what is base, and what is hypotenuse, then you can easily calculate the formula for active power and reactive power, because they are actually formulated in a similar structure to the current and voltage transfer. Alright, so what happens is, this is your actually the sinusoidal sine component of the reactive power, of the apparent power, and this is your cos component of the apparent power, right? So that's why you are already observing a cosine part here and the sine part here. So this is actually your formula which you use for active power. This is which you use for calculating reactive powers, right? And why that is, I will talk about that. Why we have a V and I, I'll tell you about this. Alright, so what happens is, this cos phi is regarded as power factor. So this is our term usually recommended as cos phi. This whole magnitude is actually called um, power factor, which is actually the ratio of the active power to the reactive power, that is the real power to the apparent power. Such uh, ratio is actually called your apparent power factor. So in that way, this power factor is useful in determining the situation of the load, what is the load and what is the supply, and let's see a little bit about that. Apart from that, this power factor is not only the ratio between the real and apparent power, but it is also similar to this power triangle is quite similar to, it's analogous to actually the impedance triangle, in which the real power gets replaced with the real resistor and the imaginary power gets replaced with the imaginary resistance, or you can say impedance, impedance and reactance, and the apparent power which is actually the resultant power, get replaced with the resultant resistance, or you can say it is the impedance, which actually carries the effect of the real resistance and the imaginary impedance as an effective. And you can apply the simple Pythagoras theorem. You have already been applying these Pythagoras theorem for impedance as well. So of course, if it is the ratio between P and S, so it this phi is also the ratio between um, R and Z, and for the obvious reason, cosine is actually perpendicular base up hypotenuse. That's why we have placed this P is actually your base upon hypotenuse. That's why equals to cos phi, right? So it's pretty obvious. And similarly, we can apply this concept for the current in voltage waveform. That is why we are having I and V. And but I do not want to go into such depth. You can always go through your textbooks and you can find out where we have derived this formula from. Is quite simple. It's not too much hectic to worry about that. All right, so let's talk some more about power factor. That power factor is actually, to recap, it's actually the ratio of base upon hypotenuse, and in both of the triangles, power triangle, impedance triangle, it was ratio between active and apparent power, and resistive and resistance, and the impedance, right? So that's a power factor. So what useful information we can get from power factor is, when power factor equals to 1, this means that your cos phi is equals to 1, and that is only possible when both of these components are equal. So they cancel out each other and you get 1. So that means in that case, your total load is actually purely resistive. There is no, in such cases when power factor is 1, there is no um, reactive power being consumed by that circuit, or you can say there is no there is a that is a purely resistive load with uh, no reactances at all. In other words, if that power factor is equals to 0, that means now this whole value of P, the active power, is 0, and the total power is actually being consumed by a reactive component. So in that case, if the power factor is 0, so that means that sort of load is actually reactive. That is only being, like for example, a pure capacitor or a pure inductor. And what in the case of when power factor was equals to 1, there was a purely resistive load like a simple resistor, right? So that is actually the extremes which are demonstrating when power factor is for a load is actually 1, then it's a pure resistive load. When the power factor is 0, it's a purely reactive load. And maybe the power factor can be between 0 and 1, which actually shows there is some part of load which is actually resistive and some part of load which is reactive, right? And for different values of capacitive and inductive, we can have different values of power factor as well. Yeah. All right. So here we came to our first post lab question, that how do we know if the reactive load is inductive or capacitive? So that's the question I was highlighting towards. So if you have a power factor, let's say, so maybe if it's purely 1, so you can say, okay, it's resistive, there is no reactive component in that, that's perfectly fine. But when you have a power factor equals to 0 and it's a purely reactive load, how would you know that that reactive load is inductive or capacitive? So how can you decide, right? So you have to find that out. That's your part of your first post lab question. And that's an interesting question. Next, some more terms, introducing some more terms. So we have already know that when we have a AC signal, let's say an AC power, let's say AC voltages. So what is actually the average voltage of a sinusoidal. So if you see the first nape cancel out second nape, because if you take the average, the area under the curve for the first nape and the second nape cancel out each other, and that's why if I take an average of a AC sinusoidal voltage signal, the resultant or the average signal would have been zero. So that is a useless information. And somehow we want to know that how much amount of AC voltage is equivalent to a DC voltage. And why we want to know that? Let's say, for example, if I have a bulb and I use 100 volts to power that bulb, it's a 100-volt bulb, let's say 100-watt bulb, maybe a 12-volt bulb. All right, so it's a 100-watt 12-volt bulb. So I need 12 DC voltage, let's say 12 DC volts to power up that bulb. But let's say if I want to power the same bulb with an AC source, so how much AC voltages would be equivalent to the DC one, right? So getting it, in order to power a same bulb, there is 12 volt 100-watt bulb which I operate on DC. Now I have to use that still the same bulb on AC. So in what ways I can choose what values of AC voltages are actually equivalent to the DC ones. So we introduce a new term here, which is called root mean square voltages, which actually are DC equivalent of AC. So this quantity which we are about to calculate will show you how much AC voltage is equivalent to the DC ones. So that is why it's also often called that RMS voltages and RMS currents are actually the DC equivalents of an AC circuit. All right, or you can say it's an effective value of the time varying current and voltage. So it's quite evident from its mathematical name that it's root mean square. So what we are about to do is, first we are about to take the square of the voltage wave, then we have to take uh, the mean, uh, and then we take the root. So it's in the form of average 1 upon t. So its mean is in represent the form of an average signals, and you might have derived that signal in your courseworks. So that when you put these time varying AC voltage source here and you square it, integrate it, divide by the sample time, and you take a square root of that, you get a simple magnitude of a number of, if you have a sine wave of, let's say, 20 sine theta, maybe yes, 20 sine 50 t. It's a time varying signal. So now we have an RMS value of a fixed number, let's say 30 volts, maybe, right? So 30 volts, or maybe less than 20, maybe it would be like 18 volts or 17 volts. So in that case, those values won't be the time varying values, unlike the AC ones. Despite this, VRMS values would show the DC equivalent of that AC, which is time varying, right? So that is how it is useful for us. So it is, sometimes this is the basic concepts which we usually want to recall every time. But as a quick method, what we used to do is, if I have a peak voltage of a AC voltage, I can directly compute it using the RMS voltage by dividing it with under root 2 or multiplying it with 0.707. And where this comes from, it came from the same formula when we take integrals of that and take root of that. So we solve that out, I'll get 0.707. Similarly, if I have peak to peak voltage, right? So peak to peak voltage for a wave, and I want to convert it into, so of course what I do is actually I divide that, multiply with 1 upon 202, or multiply with 0.37353. To the peak voltage, you will get RMS voltage. So the purpose of writing this formula is actually, these are both specific cases derived from this mathematical expression, right? So you always have to remember two things, that whenever you talk about RMS voltage, you always have to remind yourself that this is not a true voltage. Is actually the DC equivalent of an AC source, because AC is actually time varying, so you cannot predict what value of effective AC would be when it's varying its nature during the time. But you want to know the average value of AC that is being accompanied by that system, which is equivalent to the DC value, and that is actually your RMS value. represented by this formula, and you might not be able to use this formula every time, and you might not require. You can directly calculate the root mean square voltages by multiplying the peak magnitude amplitude of the wave and multiply with 0.77707 usually, and you can get this to your answers. That is how you compute root mean. So now we arise to the second part of a question, that can we measure instantaneous voltage and current from a conventional meter. So you remember the conventional meter with the full scale deflection with the deflection meter. Uh, I'm talking about the galvanometer style conventional meters, in which we have a pointer attached to a segmented spring, and the effective torque actually turn out the rotation such that the pointer indicates the value of what voltage is being. So what happens if I apply that conventional meter, pointer based meter or galvanometer based meter, to an AC voltage, right? So if an AC instantaneous voltage, let's say if I apply to the AC voltages and currents, what would happen? So this is the question. All right, then the final thing to resonate here is um, the average power, right? So the average power is basically simply as we have studied, that is was actually the product of V into Y into power factor, where cos phi is also equals to the phase difference between the angles of voltage and current. So we might not be able to touch it, but that's an interesting topic. You can always like search about it in your textbooks and online. It's a quite interesting one, but we might not be able to discuss it right now. So that happens, right? So whatever the values of RMS values for voltage and current you get, you can multiply these and you can have an average value of power that is being supplied or being consumed by an AC circuit. So this is the formula. All right, so now we arise to our first task, in which I have to I have given two mathematical functions. One is a time varying AC voltage and time varying AC current. So I have to find out average power factor in its RMS values. So quite easily, let's introduce you to the MATLAB framework and let's see how it works. It's quite simple. Alright, so this is how your simple mathematical MATLAB frameworks looks like. So this is MATLAB 2019, and there are some quite fascinating features which were not present in the previous versions, but you can always explore it. So the first thing is, on the very left of the corner, you have, when you open the MATLAB, you have the folder or the libraries that you are being continuously visiting. So whatever file you save, you can always have a look on them from here. Another one is, all right, so let's start from scratch. So we have a command window, right? All right, so whatever we do in the command window is actually, let's say 2 plus 2 plus 2. So it works like a calculator. It'll give you the answer 4. Maybe you 2 multiply by 2 or 2 multiply by 3, it gets you 6. So in the command window, whatever you do, it gives you the result immediately. Let's say if I say, all right, so if I say y is equals to 2 plus 2, right? So it gives you an answer 4. But if you see, there is another window here which is workspace, right? So in the workspace in the very left corner, you can see that y is equals to 4 is being stored. So it's acts like a workspace in which the variables you actually solve in the command window get saved. So let's say if I say x equals to 5 into 5. So I have 25, and you can see that x is equals to 25 is being already stored in this situation, right? And maybe if I can write z is equals to x plus 5, and I use a colon in the end. So colon is actually the terminator, which says that I do not want to display my answer, right? So when I press enter, there is no value of Z being printed like the previous cases because I use a terminal operator, which means that I do not want to print my answer. I already know. But at the same time, if you see in the workspace, the value of Z gets stored as 30. So it doesn't mean that it doesn't give you any answer, but it does have a value which is being stored against that, right? So 25 plus 5 gets you 30 and Z is being stored here, but it's not displayed because I've already used the terminal operator which says that I do not wish to present my answer as a separate. So that is the role of a work command window in which you can directly put inline commands and you can execute their results immediately. And all of the results are being stored in the workspace in the very left. So you might have placed it some other way. You can organize it yourself, customize it as you like it. They are movable, so you can always play with that. Another way to, so you see, if I have plenty of codes lines and I have it would be quite inconvenient to program it over command window. So that is why we need a script. So I'll go to the very left top corner and I introduce a new script. So there is one new feature in the MATLAB 2019 which is live script, which you might be interested in exploring. It's quite interesting. But we will be working on the traditional script so that we can have a unanimous sort of working. So this is an editor window, right? So it looks similar to command window. If I press this, so this is your command window in which there are double prompts showing that whatever you print here gets directly printed. But unlike command window, if turned in the off, now I have editor window. So what is the function of editor window is, unlike command window, it doesn't execute line by line. Means like if I place any command and press enter, it that executes it directly. But in the editor, you can write your code throughout and it doesn't bother if you press enter. And you have to run it separately and it will then run each of the command line by line, line by line, line by line until the whole code is finished. So it does not actually run the code in one line by line immediately, but it run the code together as a whole function, right? So you can always write whole functions here and whole your command and all your scripts here, and you can run it together to see the display on the command window. Otherwise, if you write the same code in the command window, what happens? You have to type each line, and you can't actually have multiple variables being affiliated in such a complicated manner, which is sometimes required. So let's program it. First value is let's initialize. So if I press this percentage sign, this means comments. So what is a comment? Inserting values. Right, so that means a comment is something which does not get executed by the compiler. So whatever is being written with the percentage sign is just for your reference, and the MATLAB does not look what you have printed there. It just bypasses it and go through your command, right? So let's go to our first part and all right, so let's take it from here, some initial values, and let's plot it here. So if you see, if I have put that value in the command prompt, so it might get a little bit freaking out sometimes and sometimes might not. But if I place that value in the editor window and I can still edit it, maybe. All right. All right, so I can edit it, write something here. But if I write this after execution, no. So it's locked. Once it's executed, you can't change anything, and that's why it makes it difficult for us to directly code something directly on the command window. If it's not that straightforward, we avoid it. We do it in editor window, so every time we can manipulate it or recheck it or edit it. So it's quite convenient to go for the editor window. So what happens is I inserted the values. These are the values of the magnitudes of IM and VM as was indicated. So this were the 6 and 10 as the magnitudes, and these were actually the values of 30 was the phase angle, 60 was the phase angle for the current, and 30 was the phase angle for voltages. So what V theta gets equals to 30 degrees, 30 degree angle, 60 degree angle. I converted into pi by 180 into radians, and I'll compute power factor is equals to cos V theta minus I theta, because you know that phi equals to was the difference between V theta and I theta, as was discussed in the previous slides. So you can always compute the value of power factor from here. So once you insert these values, let's compute some values. And what values were to be computed? That were actually the average power, RMS currents, and RMS voltages. So let's substitute these values here. Maybe you can type it. It's quite simple, like simply Vrms is equals to Vm divided by under root 2, or multiply it. Maybe like you can write it divided by square root 2, or you can say multiply by 0.707. It's like quite simple. You can do the same with the Im, because under square root 2 is actually the same as the uh, 0.707. 1 upon square root 2 is equals to 0.707. So you can always write that. So these are actually equivalent. You can always convert that into the RMS forms. Once you have those in the RMS forms, you get average power by getting the uh, Im into the maximum voltage, the peak voltage, and the peak current divided by the twice. And then you can always go through the values of the power factor which you have already computed, right? So you can also like put the value here directly. You don't want to recompute it. You can directly like PF. All right. Okay. So once we have these value inserted, maybe you can write like PF, and you can do not want to write that again, and you can directly say, okay, that's I have already computed the value of power factor. Let's put it that way. So now whatever value it has computed, it will substitute it here. It won't be needing to compute it again. So once we initialize the value, maybe insert the values of the good term is, or better phrases to initialize values. So maybe I initialize the values, then I computed these values, and the last part is print these stuff. So all right, so let's print the values. Print the values. All right, so when you print the values, all right, so fprint is the command which is used to print any stuff you want to display, right? So by display, that means it get displayed on the command window, right? So most of the time you have seen we have used terminal operator as colon, colon, colon. So anything won't be displaying on the command window, whatever we have computed or initialized so far. The only thing we want to display is the printing command. So let's say if I put average power, so this is the text we want to display, that is it should write average power colon, then it writes what was the value of average power which is being computed above, right here, average power. So P average power. So I'll write %f, that means it's a float, it's a category of number systems, right? So it's a sort of there's a word for it specifically. It's a type of a variable, right? So it's a variable type which is called float. You can always Google through it. So you can, that means I want to add a float here, right? Here, and that value of float is being displayed after the comma. So after comma we have average power. So that means whatever the value of average power, you could put in the value of f, percentage f, right? So what are in the next line, similarly, whatever after comma is being present is that whatever the value of power factor you have initialized, place that value of power factor into percentage as place, right? So it's a float. Whatever the value of Vrms you have computed earlier, display that value in the place of percentage f in the form of a float. So what is a float? You can always Google that. And there are other formats of variables which are available, and we might not be able to like touch it, but it's a quite interesting topic. Data types is a separate field and a good discussion topic. So every time whatever values you have computed, you want to display at this place and you have to write %f so that whatever the value is after comma being appeared here would be displayed in in the place of %f. And what this um, /n represents is it's mean the next line. So whenever you display that thing, go to the next line, and next time the power factor get printed into the next line, and you have to shift line again for RMS voltage to being displayed in the next, and same for the current. So this is how you print stuff. But the problem is, if you see, if I initialize that value, let's how to run this actually code together. So I have to press this run button at the very top. So it will ask me to save this lab. Let's say I'll say this is my lab number 10, lab 10 2. All right, lab 10A. Save it. Now it will run the whole algorithm, whatever you have right, and you can always add to path, because sometimes it creates a little problem if you have a different path available. And all of the stuff gets printed in the command window, that this is your average power is 25 something and power factor is 0.8 and RMS voltage is 7 and RMS current is 4. Right, so it's quite, but if you see all of the stuff which you have did earlier is still being appearing, right? And that's not quite a good way to do that. I want to remove all of the stuff which I have done before I run this code, right? uh, so initialize, I want to clean first my command window, and then I have to, like, right, print execute my editor window. And still, if in the workspace you see the values of x's, y's, and z are still stored, still it's not part of my code. It was something which I did earlier, and it is of no need now. So I want to remove it. So I also want to clean the command window, and I also want to clean my workspace, right? So I use certain commands as initialization commands, which you might have already seen. This is traditionally we use three commands, which is clear all. Clear alls actually clear your all of the variables uh, which are being already present in the workspace before they go through the code, and close all if there are some external windows being opened, so it close all the windows. And if you place CLC, it actually clears up the command window. CLC means clear the command window. So whatever the values you have being presented here, it actually cleans up before you run this. Whenever you run this, it clears the workspace, clear the command, close all the windows, and then it will execute further. So let's run this. So you will see all of the values in the workspace gets vanished out first initially when I run this. Alright, so you see all the values get vanished, and these new values get executed. There is no values of x, y, and z's here. Similarly, alright, so all of the values before this execution gets vanished, all deleted, all cleaned. Of just this average power equals to this and RMS voltage. So this is how we actually program stuff, or write as basic code in MATLAB. So it's quite easy and very fascinating. You can always have your patience and have your learning curve with it. There is one more part of extension of this exercise. This was task 1. The another part is task 2, in which I have two linear equations in which I have I1 and I2, maybe some currents flowing in two different loops. And by using these two equations, I have to solve them out simultaneously to get the values of I1 and I2. And of course, if these are values in J, that means these are complex currents. And of course, if they are complex currents, they have specific magnitudes and phase angles, right? If you represent in the polar convention. So it's a very simple question. It's not a question of electrical engineering. It's simply a question of simultaneous solution of two equations, right? So if you see there are two variables and there are two equations, you can solve it. That's the basic minimum requirement for it, right? And they are not homogeneous. So first part of this is exactly the same as it was before. That is clear all, close all, in all the command windows. And then you have to convert this equations into the matrix form. So you can pick all the coefficients of I1, I2 into a matrix like this one. Maybe I can write this for you. let's initialize some other file. Alright, so I'll write that. Again, I'll have to initialize or insert the values. Alright, so we are inserting the values. So this is a matrix which consists of A, whose, alright, so this is something weird. Alright, yeah, so here we go. So 600 plus 120j means this is your first component, this in the first column, first row, and this would be your first column in the second first row and second column. And when you get column, that means this is the next row. It's you shift into the next line, right? So this is now your first column and second row, and this is your second column and second row. So you can always write a matrix in a single line, right? So actually you have written this matrix in single line, which shows that these two components are single in line, and this is actually your first row and this is actually your second row, and this comma means that it's in the second line. So it's a 2 by 2 matrix, right? And similarly b is equals to 25 and 0. Let's see how where they came from. So actually b is actually equal to 25 and 0. It's actually the matrix which is the right hand side of the equation, and matrix A is the set of coefficient or the matrix consisting of the coefficients on the left hand side. So it gets A times variable I, which consists of two variables I1 and I2, is equals to 25. We have already done this sort of simplification in intermediate mathematics. We have to solve it for convert this into inverse form and Kramer's rule when we do two different methods. So here we have to find out the matrix which consists I1 and I2. I call that matrix I1, and I can find it by shifting whole of this coefficient wala matrix A to the right hand side, and when it goes to the right hand side it becomes from A to A inverse and gets multiplied with the value B, which consists of 25 and 0. So you solve it, you get the value of I, and then alright, so once I get this value here, let's compute some values. Alright, so once I have this inverse of A gets multiplied with B, I get the value of I. And by this command abs, which means absolute value, I can calculate the magnitude of the vector I, or the vector I, right? And by this command angle I, actually I get the angle in radians. So I can calculate the magnitude of the i's. I means it's a matrix consisting of I1 and I2. So I get a in MAGN magnitude, and ANG I get a two matrix magnitude and angle, in which first component of this magnitude is the magnitude of I1 and second component of this would be the magnitude of I2, and for the angle I have the first component of the angle of I1 and second component, that is I2. Let's run this and then we'll find out. Let's remove these values so that we can see what are the values. Okay, so let's save it. Lab 10B in the desktop. Alright. Alright, so we have, you can see we have value of I. So these are actually the values of I, and I converted these values of I. So how you get to the I, actually you take A inverse and multiply it V, and you get these two values. This is actually I1 and this is your I2, but these are in actually rectangular component. You have to convert it into polar. That is, you have a magnitude and phase angle, that is magnitude for I1, phase angle for I1, and this is the magnitude for I2 and phase angle for I2, and you have magnitude, but you see the angles are still in degrees, right? By some degrees, because I have converted these values in radians to degrees by this factor 180 by pi, which I think it's fairly obvious by the time you are already solving it, right? So let's display this, print these values somehow in some good manner. So first I have to terminate these, so I don't want to display useless information to being displayed there. Alright, so let's print the values. Alright, so See, all right. So you may not copy this like which I am doing. It's quite obvious and quite useless to type. It's quite straightforward, right? So whatever you want to write in the text form, you have to make it enclosed in the comma, right? So you see the whole text which you are about to display is enclosed in this comma structure, which means only this part is being displayed as your output. So that means this is your text magnitude, and there is the float which is being retrieved from the variable which you have already indicated after the comma sign. So that means write down this values of magnitude in the form of float characteristics, float variable form after this colon, and then change the line. So this is simply mentioning that to find the magnitudes, and then you move to the next line and you do the same thing for angles, right? So again, you write angles colon, and then you put the value of angles to the float and you change the line. So let's run this program again, and here you go. So now I'm not seeing any useless information. I'm just getting I1, the matrix, getting I1 and I2 in the rectangular form, and then I have magnitudes for I1 and I2 and angle 1 and angle 2 for I1 and I2, right? So this is how you simply can manipulate equations in the complex way, right? So if I've been introduced to AC circuits, so there might be you might be familiar with using KVL, KVL, and KCL, and some other techniques in the complex circuits, which include complex numbers, and that is how you have to solve it. Sometimes it's quite tricky to solve it mathematically. Sometimes we prefer to be get it solved through the MATLAB equations. Okay, so there is one more task left, and which is C. All right, so this is for from task 2, your assignment or the lab post lab task is to use I1, magnitude, exponential, angle. Write this command down and see what happens. You can write this for I1, and you can also write this for I2 set individually. So write this down and see what were your output, and you can always present your output in your post labs. So there are three components of post lab. One, the last part is actually this one, and first two parts we have already discussed. And yeah, here. So these are post. Where are you? Where are you? Here. So you need to find out the reactive load, when is inductive and capacitive, what happens to the power factor. Then same for the voltage and current in the conventional meter, what happens if you measure them from conventional galvanometer type meter, right? So yeah, that was an interesting lab, and that was actually a basic introduction to the MATLAB. Another features that I want to introduce to MATLAB is there are a lot of options out there in MATLAB 2019, which is plot, some additional application, how to publish your stuff. So there are a lot of components. All right. So if you see in the home tab, there is one more tab which is Simulink, right? So in the next lab, this Simulink block will be used in lab number 11, and in that lab, we will generate some models and see how we can also use MATLAB to get to our results by modeling perspectives, right? So what we have did in our lab number 10 is to get to our answers and get to our results by means of coding. But in the next lab, we'll go through model-based approach. So we have to model that whole thing, and then we can go through it, right? So this is for the lab, and see you in the next lab. Thank you.